also there has to be as many pops as there are pushes, otherwise what will happen? So, there will be a mismatch, and in that case the return address picked up by the this return instruction will be in problem. So, let us try to see like how this thing can happen. Say so as you know that when I am going to a subroutine, so this stack top, so if this is the stack top, so it contains the return address. So, these two locations they will have the return address, they will have the return address. Now, after that what at the beginning, so I have done say one push. Okay. So, this push say D. So, the D pair has been pushed here. So, this is your E register, this is the this is the D register, this is the E register that is there. Now, at the end, so if we forget to pop the D and we directly put a return instruction here, then in the execution of return instruction what will happen? So, it will try to take out the content of the two topmost locations from stack and put them into the PC. So, as a result, when this return is executed, the PC register will get the original content of the DE pair, and which is definitely not the return address. Okay. So, that way the program will return to some arbitrary location. So, that is why we said that this is the other caution, that this number of push and pop must match. Okay. If there is a mismatch, then or it may so happen that I have done say 5 pushes at the beginning and 6 pops at the end. So, if I do 5 pushes and 6 pops, and then what will happen is that this return address has also been popped out from the stack. So, the next location whatever is there, so that will be some garbage value, and that that value will be loaded into the PC when we are trying to return. So, this push and pop must match, number of push and pops they are ordered, and these things should match. So, we have to be careful in that sense. So, these are the things that push pop should be used in opposite order, and the number of this push and pop must match, and it is not advisable to place this push and pop inside a loop, because it may so happen that a loop may exit via different ways, and it is it may not be ensured that in all the exits same number of push and pops are encountered. So, that way the return at the stack content may become erroneous, and this return address may be popped out wrongly. So, there is another version of this call and return instruction which are known as conditional call. So, just like conditional jump, so we have got conditional call, like we have got the CC instruction. So, this will call the subroutine if the carry flag is set. So, call subroutine if carry flag is set, then CNC it will call the subroutine if carry flag is not set. So, we have got similarly we can have say CZ call if the 0 flag is set, CNZ call if the 0 flag is not set. This way we can have many variants, like then similarly for the return also we can have RC. So, return if carry flag is set, and RNC return if carry flag is not set. So, this way we can have different variants, whatever combinations you have for jump instruction, all those combinations can be there for the call instruction as well. However, as a general design practice, so if you are looking it from a software engineering angle, so a proper subroutine should have some important properties. The first one is that it is only entered with a call and exited with a return instruction. So, the subroutine should have a call instruction, and so it should be entered via a call and returned via a rate. So, that is it has got a single entry point and it has got a single exit point. So, if we do not follow this, then what will happen is that say I am writing a subroutine. So, this is my subroutine, and there is no harm, like so say instead of from somewhere here I put a jump instruction, jump to address say L1, where L1 is somewhere outside the subroutine, L1 is somewhere here, but actual the return is here, but in some conditional execution of the code it jumps from this L1. Maybe instead of a simple jump, it may be a jump on carry or something like that, some conditional jump, and it jumps out of the subroutine. Now, if this thing is done, then the major difficulty that you have is that now the stack content becomes inconsistent, because the stack will still have the return value stored in the init stop. Okay. So, that is somehow we have to ensure that the stack pointer value is modified, so that those return value gets discarded. Or if this is a label say L2 in my program, in my subprogram or subroutine, then from outside, so you can have something like so normal entry, if the first entry has got the label say subroutine sub, say suppose the name of the it has got the name SU. Okay. Then what will happen is that you will get normal exit into entry into this subroutine is like call SU. So, it will be calling the subroutine SU and putting going there. But as such, in this is the main program. So, there is nobody is restricting you to write a statement like say jump L2. So, we will jump inside the subroutine. So, instead of going via this proper entry point, so you can jump inside the subroutine, and if you do that, then the difficulty is that the return address is not saved in the stack. So, when the rate instruction will be executed in future, so rate will not be able to return to a proper address until and unless you take enough care to put the return address into the stack separately. Okay. So, these are not a very good programming practice. So, ideally you should have a single entry point and single exit point in the subroutine, and the subroutine should be entered through that entry point only, and it should be exited in that entry through that entry point only. So, this is what is said here, that according to software engineering practice, a subroutine is only entered with a call and exited with an RET and has a single entry point. So, do not use a call statement to jump into different points of the same subroutine. So, okay. So, or you can have you should also have a single exit point, should not be, there should be only one return statement from any subroutine. So, if you have got multiple return statements, so that makes the readability of the program difficult. So, we should try to redesign that subroutine, so that there is only one exit point. So, that will help in making the program easily understandable. So, following these rules, there should not be any confusion with push and pop usages also. So, push and pop, so then their number should match and all that. And so, if we follow all these rules, then we will be able to design good subroutine. Next, we will go into another very important concepts in the processor design, which are known as interrupts. So far whatever we have discussed in this course, so there we have got the processor, and processor it gets the next instruction from memory, executes it. So, there is no way by which we can tell the processor that something has happened in the outside world and something emergency has to be done, something exceptional has to be done. Like say if there is a if I am having a program that controls the operation of a plant, then it controls the conveyor belt, etc., etc. So, all those parts are routine. So, they are going on at some regular intervals of time. So, my processor is generating control signals through some programs in that way. But suppose there is a fire that is detected, okay, there is a smoke detector. So, smoke detector detects if some fire, some smoke, or there is a possibility of fire. So, now whatever the processor was doing, so it was controlling the conveyor belt. So, it should be told immediately that some fire handling routine has to be executed, which will activate the fire tenders, or if it will send a call to the local fire brigade office, like that. So, that has to be done. So, that is basically the interrupt. And in our day to day life also, suppose I am reading a book sitting in my room. So, that is the normal process, or say some person comes and presses the doorbell. So, that is an interrupt. So, I have to stop the reading the book, I have to go open, find out what that person wants and all that, do all those operations, and then again after some time when that interaction with the person is over, I will come back and read the book. So, similarly, so if in the processor also the interrupts will be like that. So, when such situation occurs, that particular service has to be done or particular routine has to be executed by the processor, and once that processing is over, the processor should resume whatever it was doing. So, interrupt is a process where an external device can get the attention of the microprocessor. So, normally, so this interrupt has to be initiated by the IO device. So, processor will not initiate it, otherwise what, like if I have connected a keyboard with the processor. Now, normally this keyboard is operated by human beings. So, they are much slower compared to this electronic components like processors. Now, if the processor is operating like this, that it continually scans whether any key has been pressed by the user and then takes some action, then a major part of processor's time will be spent just to do this polling, like if any key has been pressed, finding out that. A better design is like this, that whenever the user presses a key, the processor will be informed that a key has been pressed, and then accordingly the processor will try to understand which key has been pressed and take some action on that basis. So, this way these interrupts are actually originating from the IO device. So, IO device, they will send an interrupt to the processor, and this whole process is asynchronous. So, asynchronous means it is not synchronized with the CPU, the processor clock. So, it is not mandatory that this interrupt should occur at the clock edges and things like that. So, it is totally asynchronous, it can come at any point of time. So, whether it will be answered by the processor or not, that depends on many other things as we see it slowly, but the occurrence is asynchronous. There can be two types of interrupts. Some of the interrupts are called maskable and some of them are called non-maskable. So, maskable means there is interrupts, they can be delayed. So, you can I can say that for the time being I do not want to get interrupted from this source. Okay. For example, as going back to the human being reading a book and the doorbell rings. So, if I want that if I want that okay, I should not be disturbed at this time, then I can disable the doorbell switch, so that even if that doorbell is pressed, the bell will not ring. So, that way we can make that that doorbell a maskable interrupt. Okay. On the other hand, if there is a power failure or if there is some say again say the smoke detector that detects fire. So, that sort of thing they are non-maskable. So, we should not be able to modify them. So, we should not be able to delay them. So, that should be taken care of immediately. So, that way in a processor also, depending upon the type of activities or type of IO devices that you connect to the system, some of the devices are so critical that we cannot stop them from interrupting the processor, and for some of them we may they are not of that much importance. So, when the processor feels that it can accept interrupt from those devices, it will unmask those devices, those interrupts, and then only the interrupts can be sent from those devices, otherwise not. So, that is one type of classification. Another way of classifying interrupts is by vectored and non-vectored. Like as I have said that whenever an interrupt occurs, so what is done is that the interrupt has to be serviced. Now, how a processor will service interrupt? So, processor should execute a piece of code which is pre-decided. Then this processor will be like as I said that whenever this smoke detector sends an interrupt that a smoke has been detected, the code for initiating the fire tenders, that should start. Okay, for activating the fire tenders, that should start. Similarly, the code for starting informing the fire brigade, that should start. So, that way we can say that so those addresses, so those are the addresses for the ISR. These are called interrupt service routine or ISR in short. So, these ISRs are to be loaded into the memory, they are already available in the memory. Okay. So, before the system starts, the programmer has to ensure that the interrupt service routine for all the interrupts are already in place in the memory, and for some of the interrupts this address, the address of the ISR is fixed. Okay. So, there are some fixed location where the corresponding ISR should be loaded. So, whenever that interrupt occurs, the processor need not check for the ISR address. So, it knows where to go for the ISR. So, it immediately goes to that address. Other possibility is that they are non-vectored interrupt, that is in this case when the interrupt has occurred, the processor will ask the device to tell the interrupt service routine address. So, processor in some way it will provide the interrupt service routine address, and the processor will jump to that particular interrupt service routine. So, this way there can be two types of interrupts. One is vectored interrupt, where the address of the service routine is hardwired. So, it is known to the processor, it is fixed by the processor designers. On the other hand, there are non-vectored interrupt, where the address of the service routine needs to be supplied externally from the outside world. This interrupt address should be supplied. So, this is an emergency signal. So, microprocessor should respond to it as soon as possible, because that is why this has been put as an interrupt. So, we should be able to respond to that interrupt as soon as possible. So, when the microprocessor receives an interrupt signal, it suspends the currently executing program and jumps to the interrupt service routine to respond to the incoming interrupt. So, as I said that every interrupt has got a corresponding interrupt service routine. So, the processor, it was doing something, it was executing some program, all on a sudden the interrupt has occurred. So, the processor has to suspend the program that it was currently executing and go to that interrupt service routine, execute that interrupt service routine, and once the interrupt service routine is over, then it should resume the original operation. So, that is how this sequence of operation should take place. So, the time at which you respond to the interrupt, so that is determined by, it may be immediate or may be delayed. Okay. So, if it is if the interrupt is maskable or the interrupt is non-maskable, depending on that this response time may vary. And so, there are if it is immediate, if the response, if it is not masked, the interrupt is not masked, then it is expected that the response will be immediate. If the interrupt is maskable, then the processor may find that interrupt sometime later when it tries to remove the mask for the interrupt, and then at that time it may find that some interrupt is waiting, and it will go and go to the interrupt service routine at that time. So, that way whether it is masked or not, so based on that the interrupt service may be immediate or it may be delayed. So, there are two ways for redirecting this ISR to the ISR depending upon the vectored or non-vectored. So, that we have already seen that if an interrupt is a vectored interrupt, then the interrupt service routine address is known to the microprocessor. So, it can immediately go to that interrupt service routine. On the other hand, if it is a non-vectored interrupt, then the interrupt service routine is not known to the microprocessor. So, the device will have to supply. So, at least the microprocessor has to wait for some time for the device to come up with the interrupt service routine address. So, that way some cycles will be spent in getting the interrupt service routine address, and that way the response will be delayed by that much time. So, that this discussion is true for any processor. So, 8085 is one example. So, they will see what are the types of interrupts that 8085 has, but in general any processor will have maskable interrupt, non-maskable interrupt, then it will have this vectored interrupt, non-vectored interrupt, like that. So, in case of 8085, so there are a number of interrupts, some of which are maskable, some of which are non-maskable, and these maskable interrupts are controlled by one flip flop which is known as interrupt enable flip flop. So, this interrupt enable flip flop is not directly accessible by the user, but the user can use the instruction like EI and DI to enable and disable this interrupt enable to enable and disable the interrupt. So, EI will enable interrupts and DI will disable interrupts, and this EI and DI, so they actually affect this interrupt enable flip flop, and by setting EI will set it to 1 and DI will set it to 0. So, that way this EI and DI will occur. So, there is only one non-maskable interrupt in case of 8085. So, that does not get affected by this EI and DI. So, that is we will see that slowly. So, non-maskable interrupt will not get affected by EI and DI, only the maskable interrupts will get. So, the interrupt enable flip flop has got effect on non-maskable interrupts and not on the maskable interrupt. So, there are 5 interrupt pins. So, if you remember the pin diagram that we have shown for this 8085 processor. So, there are 5 special pins. The first one is the INTR. There is a pin marked as INTR. So, this is the only non-vectored interrupt. So, non-vectored interrupt means the interrupt interrupt service routine address is not known, and when this interrupt occurs. So, if a device which is connected to this INTR line, so may send an interrupt to the processor via this INTR line, and when this INTR interrupt comes, since it is a non-vectored interrupt, so the processor will go to a particular execution cycle where it will expect the device to provide it with the ISR address, and after getting that ISR address, the processor will go to that ISR. So, INTR is maskable interrupt. So, this is it is so INTR is a so one thing is it is non-vectored. Another feature that we have got is that it is maskable. So, this EIDI instructions can be used for enabling and disabling interrupts. Then this there are 3 more pins, RST 5.5, RST 6.5 and RST 7.5. So, they are automatically vectored interrupts. So, for them the ISR addresses are known to the processor. So, the processor will branch to a particular address when these interrupts occur, and all of them are maskable. So, this 5.5, 6.5, 7.5, all these interrupts are maskable interrupt. Whereas, there is another interrupt pin which is known as trap, and this is the only non-maskable interrupt in 8085, and it is also a vectored interrupt. So, the ISR address for trap is known and it is non-maskable interrupt. So, if you are designing a system with 8085 as the underlying processor, so you can understand that you have to, if you have to going to connect a number of devices to the system, then they can be connected to the INTR or they can be connected to these RST lines, and the most important of all these interrupts, so they should be connected to that should be connected to the trap line. Typically, we serious conditions like power failure and all that. So, they are connected to the trap line, so that this trap service routine. So, the power goes, then the system is held on the battery. So, the system should try to save all the critical data first for the system. So, this trap service routine may be doing that. So, it will take a note of all the critical data that are there in the system, their values and all that. It should copy them onto some save locations, and then it should go into a power down mode. So, that way this trap can be used for the situation which is very critical. So, to summarize, so we have got this INTR which is maskable and it is not vectored. 5.5, 6.5, 7.5, they are all maskable and they are all vectored as well, and this trap is a non-maskable interrupt and it is a vectored interrupt. So, the ISR address is known. Now, what are these ISR, the vector address and all that? So, where can we find these vectors and all that? So, an interrupt vector is a pointer to where the ISR is stored in the memory. So, when I say I have said that 5.5, 6.5, so they are all vectored interrupt. So, vectored interrupt means that their address should be known. So, all interrupts vectored or otherwise they are mapped onto a memory area which is known as interrupt vector table. So, they are normally located in the page 00, that is the in the first 256 locations, all 0 to 00 FF hex. So, this holds the vectors that redirect the microprocessor to the right place when the interrupt arrives. So, what happens is that when a particular interrupt occurs, say 5.5 occurs, so then there is a fixed address to which the processor will jump to, and that address range comes in this range 00 to FF hex, and in that part, so you can have your ISR for this 5.5, and we can accordingly execute the ISR there. And it is divided into a block, this IVT area, there is 0 to FF, it is divided into blocks, and each block is controlled, each block is used by the interrupts that to hold its vector. Okay. So, I will take an example and say that way. So, it is like this, that so it is this interrupt vector table. So, it is like this, that say this RST this interrupt RST 5.5 has occurred. So, what the processor does is that this value is multiplied by 8. So, 5.5 into 8. So, that is 24. So, it will come to the memory location 24, and 24 onwards it will expect the interrupt service routine for 5.5 to be located. Now, so this after 5.5 I have 6.5. So, 6.5 will start at 27, say that is sorry 6.5 will 5.5 will start at 5.5 into 8, 5.5 into 8, that makes it 44. So, it will start at 44, and 6.5 will start at 48. Okay. So, so that way, that is we have got only a few bytes. So, we have got only a few bytes for doing that. So, 5.5 into 8. So, this makes it 40 plus 4, 44, and say 6.5 into 8. So, this makes it 48 plus 4, 52. So, if this 5.5 interrupt occurs, so if this is my memory, so it will jump to the address 44. So, it will jump to the address decimal 44, and if it is if 6.5 occurs, so it will jump to the memory location whose address is 52. So, you see that between these two, so 44 to 51, so we have got 6 plus 7, 8 locations. So, we have got 8 locations in between for holding the interrupt service routine for 5.5. Similarly, for 6.5, after that 7.5 will come after 8 locations. So, we have got another 8 locations to hold the interrupt service routine for 6.5. Now, if the interrupt service routine is very small for a particular device, then it may be contained in that 8 bytes. Okay. And if it is not, which is normally the case, normally we do not have so small interrupt service routine that it can be held in 8 bytes. So, what we do? We put a jump instruction here, jump to some memory address. We put a jump instruction there, so that this actual ISR for this 5.5 may be located from memory location 2000. Okay. So, what we do? We put a jump 2000 instruction here, and this requires only 3 bytes. So, the coding of this instruction requires only 3 bytes. So, that is good enough for me. So, I use only 3 bytes here and put the code of jump 2000. So, that when the interrupt occurs, the processor will come to this point. So, it will get this instruction jump 2000. So, it will jump to the memory address 2000 and execute the ISR code there. Okay. So, this way we can handle large ISR codes in these smaller memory locations, smaller sized interrupt vector table chunks.